Hello, Upper Six. So the last lesson we looked at distances and brightnesses of stars. This next lesson we're going to continue looking at measurements that you can take from stars which tell you about the physics of what's going on with stars. There's going to be another lesson after this on stars which will be looking at how stars evolve and how they are born, live and die. But before we get onto that, let's go through today's work. Last lesson I talked about what you would if you were sitting outside looking at the sky. As a physicist, what questions might you ask about the stars that you see in the nighttime sky? So one question would have been, how far away are they? Another would have been, can we measure how bright stars are, or compare how bright stars are? The third thing that we're going to look at is something that you probably haven't noticed when you've looked at stars, if you've ever looked at stars, which is their colour. Now, at first glance, when you look at stars in the nighttime sky, they all look white. But actually, that's not the case. If you look very carefully at stars, particularly if you take a photograph, you can often see it a lot better on a photograph. All the stars are actually different colours. They range from red through orange, yellow, white, and some of them are slightly bluish white. Our star, the Sun, although we often think of it as yellow, it's actually a bit closer to white. It's really white with a slight tinge of yellow. It looks yellower at sunset just because the sunlight is shining through the Earth's atmosphere, and some of the bluer wavelengths get scattered, and it makes it look a bit redder. In fact, our sun is pretty close to being white. It's sort of yellowy white. So all stars are different colours, and what's the reason why stars are different colours? Well, this goes back to something called blackbody radiation. Now, a blackbody is, I suppose, a theoretical construct. A blackbody is a perfect emitter and absorber of radiation, of thermal radiation. It absorbs 100% of the thermal radiation that hits it, and it will emit perfectly radiation from its surface. It's a perfectly black surface. Why is this a useful idea when you're thinking about stars? Well, to a first approximation, stars are like blackbody emitters of radiation. So if they're at a certain temperature, they will emit a range of wavelengths of light because they're black bodies. Now, there's a whole theoretical branch of physics to do with blackbody radiation and what causes blackbody radiation. About 120 years ago, a very bright scientist called Max Planck explained why black bodies emit the range of wavelengths of light that they do when they're at a certain temperature. Luckily for you, that's beyond the scope of the course. You don't have to explain what causes blackbody radiation in terms of the distribution of the different wavelengths. What you do have to do is look at the basic rules of blackbody radiation and apply them to stars. Now, what do I mean by blackbody radiation and the spectrum from a black body? Well, I've actually drawn a graph here, which I'll show you in a minute. If you take light from an object that's at a certain temperature that's being emitted because the object is hot, the photons that are coming from the surface of that object won't all be at the same wavelength. They'll cover a spread of wavelengths. So you'll have a spectrum of wavelengths. Now, it's very familiar to you, hopefully, that if you shine white light through a prism, it splits the white light up into a rainbow going from red to violet, red being longest wavelengths of visible light and violet being the shortest wavelengths of visible light. And it's the same idea. Blackbody radiation covers a range of wavelengths, not just the visible part of the spectrum, but also the invisible infrared and ultraviolet parts of the spectrum as well. And you can measure a spectrum by measuring how much intensity of radiation is being emitted at each of the different wavelengths. And it turns out that if you do this experimentally, you get a peak wavelength. The intensity starts very low at short wavelengths. It goes up to a peak wavelength where most of the energy is being emitted, and then it gradually drops down again. And this curve, which is explained theoretically, is called the Blackbody radiation curve. So I'm going to show you now a graph of the Blackbody radiation curve. So here it is. So what we've got on here, just to explain, because this is something you might be asked to explain in an exam, is on the y-axis you've got intensity of light. So that's how much energy is being emitted at a certain wavelength. And then across the x-axis you've got the wavelength. So starting from 0, and in this case I've drawn it up to about 2000 nanometers. So the actual range of visible light is quite a narrow range. So these are the visible wavelengths within this shaded in band. Shorter wavelengths than that are ultraviolet, and longer wavelengths than that are infrared. So what I've drawn here is 3 curves which represent the spectra of 3 different objects at different temperatures. So the solid curve is a body at about 6000 Kelvin, which is actually similar to the temperature of the surface of the sun. And what you can see for this body is that it reaches a peak wavelength of just under 500 nanometers. So actually the peak of the wavelength of light that it's being emitted is in the middle of the visible light band. So a lot of the energy is being emitted as visible light if you've got something which is this hot. If you then move to something that's cooler, so these are the 2 dotted lines. So the first dotted line there, we've dropped the temperature from 6000 Kelvin to 3000 Kelvin. 2 things you will notice. Number 1, the peak has moved to a higher wavelength. It's actually now in the infrared part of the spectrum. It's still emitting some light. Okay, it's still emitting some visible light, although it's emitting more red light than blue light. So this object will appear to be glowing red rather than glowing white hot. And the other thing you'll notice is that the total amount of energy that's being emitted is less. Okay, it's fairly obvious, but if you look at the area under the graph, if you integrated the area under these curves, you get the total amount of energy being emitted per second by the object in all directions. And you can see that as you get cooler, that reduces, and the third dotted line is 2000 Kelvin is even cooler, and you can see it's the wavelength has shifted, the peak wavelength has shifted to an even higher wavelength, and the area under the curve is even less. So 2 things to remember. Okay, as you change the temperature, if you reduce the temperature, the peak wavelength increases, and the total amount of energy being emitted also decreases. Now, theoretically, you can derive 2 equations which describe exactly what's happening here, and they're called Wien's law and Stefan's law. And these 2 laws are going to be, they will be on formula sheets in A-level physics, but also you have to learn how to use them. So the first one is Wien's law. Now, Wien's law, really simple. It tells you where the peak wavelength is for a black body spectrum. So the peak wavelength is inversely proportional to temperature in Kelvin. So peak wavelength times temperature equals a constant. Constant is 0.029, sometimes called Wien's constant. So that's the first rule that you have to learn when you're dealing with blackbody radiation and stars. So that's Wien's law. The second law is called Stefan's law, which is the one in this bubble here, which tells you how much light is emitted in total, or how much, I should say, how much electromagnetic radiation of all wavelengths, including light and ultraviolet and infrared, is emitted in total. Now this formula is P, which is power, equals a constant, it's called the Stefan constant, times A, which is the surface area. Obviously, the bigger the surface area, the more is going to be emitted, times T to the power 4. Okay, that is T to the power 4, which is a huge dependence on T. A very small increase in temperature, you get a lot more energy being emitted. So these two laws together can actually tell you quite a lot about the physics of what's going on in a star. Because if you measure the spectrum of a star, so you put starlight through a prism, or more accurately these days through a grating, you can split the light up. You can spread it out into its different wavelengths. You can measure how much energy is being emitted at the different wavelengths. You can first of all see the peak of the wavelength that's being emitted. And from that, you can get the temperature of the surface of the star. So if you did it for the sun, you'd get about 5,700 Kelvin. So you get the peak, you get the from the peak wavelength, you can use Wien's law and get the temperature of the surface of the star. You can then go and use Stefan's law, and if you know what the power output of the star is, which you can actually get from measuring its absolute magnitude, you know what this constant is, you know what the temperature is because you've just measured it through Wien's law. Stefan's law will actually give you the surface area of the star, and if you assume that the star is a sphere, area would be for a sphere is 4 pi r squared. So you can actually work out the radius of the star. Remember, the stars are too far away, you can't actually directly image them in the way you can image planets. So there's no direct way, really, of measuring what the size of a star is. But from this, you can actually measure the size of the star. You can tell whether the star is very big, much bigger than the sun, a giant star, or whether it's a dwarf star. And you can answer the question, how hot is the surface? So two really important physical things that you can get by approximating the spectrum of a star to a Blackbody curve. You can measure the temperature of a star, and you can also measure the size of a star. Or you could also, of course, compare the sizes of two different stars if you know their relative absolute magnitudes. Okay, so that's Blackbody radiation curves. The other thing that we need to cover in this little lesson is how we classify stars according to their spectra. Now, the Blackbody curve, I'll put this down for a minute. So the Blackbody curve is a theoretical curve that shows the radiation emitted by a perfect emitter of radiation. In fact, stars are not perfect black bodies. We know this because if you take the spectrum of the sun or any other star, you don't actually see a perfect spread out rainbow of light. So a first approximation you do, but if you use an accurate instrument to split up the light into different wavelengths, yes, you will see a continuum of light from red to violet, but superimposed on that you will see dark lines. So there'll be gaps where less energy is being emitted at a particular wavelength. So these dark lines, of course, you've studied this before in the lower six, these are absorption spectra. So what's happening is the bright light from the surface of the star is passing through the cooler atmosphere, and photons of particular wavelengths, which basically corresponds to particular energies, are being absorbed by atoms in the atmosphere of the star, and they're exciting those atoms, or they're exciting electrons within those atoms from one energy level up to another energy level at a particular wavelength that corresponds to that gap of energy levels. And because these particular wavelengths are being absorbed, you see these dark lines in the spectrum of stars. So actually the Blackbody spectrum is an approximation to what a star's spectrum actually looks like. You may think, well, that messes up Wien's law and Stefan's law and so on, but actually these dark lines are really, really helpful. They're helpful in quite a few ways. One thing that they're helpful for is that they can allow us to probe the chemical composition of the atmosphere of the star. Of course, different elements, you would have different energy levels, different wavelengths that are being absorbed. So you can identify, there's hydrogen, there's sodium, and so on. There's calcium in the atmosphere of this star. So you can do a chemical analysis of the atmosphere of a star from its spectrum. But the other useful thing as well is that you can measure the temperature very accurately. Actually, it's rather better than using Wien's law. And the reason for this is because different transitions in atoms actually happen at different temperatures. So stars that are different temperatures actually have very different absorption spectrum. You see different lines at different wavelengths. So, for example, the coolest stars, you have molecules forming in their atmosphere. Molecules break up at higher temperatures. But cooler stars, you have molecules like vanadium oxide, titanium oxide, and these have absorption lines that correspond to these molecules that form at low temperature. So you can identify a low temperature star by seeing these molecular absorption lines or absorption bands in the spectrum of the star. As you get to hotter stars, you see different things. So as you get to a slightly hotter star, you will see the absorption lines of neutral metals such as sodium. So the sun's spectrum has quite prominent spectral lines of sodium. Hotter stars, you start to see spectral lines of ionized metals such as sodium. And then the hottest stars of all, the really hot stars, you see spectral lines of hydrogen and helium. So astronomers use these different spectral lines that they saw in the atmospheres of stars to actually classify stars into different spectral classes. Now, unfortunately, there's not a logical really way of remembering these spectral classes, but you do need to remember them. It is one of the things on the specification. So they run from the hottest stars, O. It actually stands for Orion class because a lot of the stars in Orion are this class. You have O, and then B, and then A, F, G, K, and M. So O, B, A, F, G, K, M. M is the coolest stars. So I believe M stands for molecules. So these are the ones where you see molecules in their atmosphere in the absorption lines. So I said there's no really easy way of memorizing these 7 different spectral classes. Some people use a mnemonic to remember them. I think OBA, fine girl, kiss me, or fine guy, if you prefer, is one that's quite often remembered. There is actually some history about why these letters are organised the way they are, but I'm not going to go into that. So these are the 7 spectral classes of stars. The Sun is a type G star. So M stars are very cool. They're red, hot. K stars are orange. G stars are sort of yellowish white. F stars are white. A stars are white as well. And then you're getting into the really hot stars. The B stars and the O stars are bluish white. So as you get to the hotter stars, more and more of the energy, the Wien's law suggests, more and more of the energy gets emitted at bluer wavelengths. In fact, what I may do is I may attach to this lesson a short video I did with the Year 10s a couple of weeks ago, where I showed them radiation from a light bulb as I turn the light bulb slowly up, and you can actually see the light getting bluer, or at least getting less red as the tungsten filament gets hotter. It's quite impressive. So I may add that Year 10 YouTube clip onto this lesson as well. So that's basically it. Now there is a table that you do have to learn with the spectral classes. So you do have to be able to roughly describe which elements and metals and so on are seen at the different classes, and also what temperatures the different classes correspond to. So that's the spectral classes of stars. Next lesson, we're going to look at what this all means. We're going to try and put it all together, because we now have a lot of information about stars, We've taught you about, you can work out how bright stars are, their absolute magnitude. You can also work out from their spectral class how hot stars are as well. What's actually going on with stars? You know, what are the patterns that link these different objects? And when you find the patterns, you can start to understand the physics that actually underlines stars and the processes that are powering stars. Okay, so that's it. As usual, there's going to be some notes. As usual, I'll give you a few questions. It is a bank holiday weekend, so I'm not going to give you a huge number of questions to do, but I do expect you to do these. So that's it. I hope you have a good weekend, and I will speak to you soon. Thank you.